So we are going to start a very interesting topic in the interpretive aspects of how we can interpret what we construe as quantum reality. So there is no hard and fast, or there is not a consensus what is quantum reality. In the construction of this, in the departure from, even though it's old now, more than 100 years, the transition from classical to quantum in that sense, and how do we perceive quantum as apart from its operational and what I should say, pragmatic reasons. Working physicists may not be interested in those questions, which will fundamentally somehow touch on how we say, how we construct the epistemology of things in general and quantum mechanical epistemology. So in that context, the many world interpretation of quantum mechanics. So it's one of the interesting chapters in how we interpret quantum mechanical reality, and it has been so the we're going to follow. This is written by, so these people have been David and Neil Graham. So this is a document written by them, and more or less it's their exposition how since they have been contributors of this understanding this question. So we are going to follow these discussion regarding the many world interpretation of quantum mechanics. So in the first part, we are going to start with the theory of universal wave function. So this is the introductory part of it. Before we are going to interpret what are the many world interpretations of quantum mechanics. So how we arrive at this theory of universal wave function. So we are going to see, before we are going to characterize this thing. So there are some unwritten rules, or there are certain implicit assumptions which are given for how we talk of quantum states. Before we are going to just see the nuances, or what I should say, difficulties in why should we accept these things. So before that, so first, how we define a physical system. A physical system is completely described by state psi, which is meant in quantum mechanical sense. It's part of that Hilbert space, as element of Hilbert space. Mathematically, it's infinite dimensional vector space. And furthermore, this gives gives information concerning probabilities of the results of various observations which can be made on the system. So this is can be made on. So this much is known. System. So physical state is described with state psi, which is part of some Hilbert space, and there are configurations which will tell. So they will describe. So we are going to. So this is a physical state of a system, which is described by state psi, and these are the information concerning the probabilities of the various observations about the system. Now, state psi is thought, so here we are going to emphasize, it's thought to be objectively. So here this word objective is to be emphasized, is to objectively characterizing state of physical system. So state psi is thought to be objective. Objectively in the sense that the reality of that state psi, whether prior to measurement or after measurement, it exists and it's objective in that sense. It's not that measurement will change it in some sense, or it's inaccessible in that sense. That's such that we cannot, its objectivity cannot be ascertained. And at all times for an isolated system, so again we can also this thing has to be what I should say, seen in the context of an isolated system. The system which is not interacting with the observer or measurements of the observer or the universe at large. That isolated system can be universe in itself. That's besides the point. But the thing is that this objectivity is somehow related with the system being isolated. And this state psi will change in a causal manner. So long we are going to maintain the isolated character of this system. So change in the same, so causality as such is maintained in this isolated system. We assume that causality should hold independently for this isolated system in which we have defined this state psi. And this will obey a differential equation. Obeying a differential equation, the way normally you see evolution state, the way we have an evolution of a particle or evolution of a state from a given point to another in a causality. There is no cut. Now, there are different. Now here we are going to make an interjection. Interjection is interjection. So we have defined, we have set the stage. The interjection is, now there can be two processes, process 1 and process 2. So even if now if we are going to introduce some change in that state psi, so which will introduce some discontinuity. So the discontinuous change brought by the observation of quantity with eigenstates phi1, phi2, so on and so forth, in which state psi will be changed to 5G with probability psi I 5G square. So you can have the discontinuities which can be associated for a state psi going to phi 1 or psi going to phi 2 or psi going to phi 3, so on and so forth. So the probability will be given by the inner product of psi and phi. This is J. J can go from 1, 2, 3, so any state. So this is one interjection, you can say it, a plausible interjection. So in the same sense, there's another process 2. So the continuous. So here we are going to use the continuous as a thing. So even though the change is there, the continuous deterministic change, which is going on the state function psi of an isolated system. Often we are taking the system isolated. Isolated system in the time t can be given by the wave function. So just like we have Schrodinger time dependent or time independent Schrodinger equation, d psi by dt is t is given by u of psi, where u is a linear operator. So in quantum mechanics, the idea of linearity condition or non-linearity condition, it becomes important. So the evolution of wave function psi for this isolated system, it is going to have there will be a deterministic and continuous change, this wave function psi. So it will change vis-a-vis this. U can be some linear operator. So now there are a couple of questions regarding these constructions, these sort of constructions, or there are some curiosities which need to be, which ought to be addressed. So we have constructed an isolated system. So the question of consistency. So the question of consistency arises for a system if one contemplates that observer who is outside this isolated system and plus his object system as can be considered as single but composite system. So in this question, this can be extended to whether the observer is single or there can be more than one observers, or there can be simultaneous observers of the same equal weight, or there can be different observers sitting here and there. Their measurements may vary. So in one case, if we take observer A performing measurements upon system S. Observer performing measurement on system S in the totality A plus S in turn forming object system for another observer. So in case of there is an observer A which is performing measurements on the system S, this isolated system S. So you can have A plus S can still form a system, but you can still construct a system outside it, and that for that observer this becomes an object system. Observer, this also becomes object system. Means this isolated system plus observer, this will become a system for another observer, or then it can become the system for another observer, and so on. So depends upon your construction. And now, if we deny the possibilities of these, means use of means this observers, if you deny that he is having a quantum mechanical description or wave function being satisfied, this is satisfied by a wave function, which may contain not only observers. So observer here is a acronym. You can also use measuring apparatuses in that sense, or apparatuses and measurements in relation to observers. So sometimes measuring apparatus and observer can merge. But we would have to have a preferred position. Whether we are going to have a measuring apparatus or observer, and there can be more than one descriptions regarding the same, which will take into account these isolated system plus observer or observers. So now, so if we allow B to be a quantum description to A plus S, so we can have a wave function, we can have a wave function, psi. We can allow, if we allow B to have a quantum description, B means the observer who is observing this system plus that isolated system, A plus S. If we allow B is a quantum system, quantum description, so he is a quantum observer, so he is observing system A plus S, then the state will be A plus S. And so long as B does not interact with, so long as B does not interact with A plus S, it changes causally, it changes causally by processes 1 and 2. Processes 1 and 2 we have defined previously. Processes 1 is means we believe that there is in an isolated system causality is causality sustains, and we have a d psi by dt is equal to operator dependence, which has a linearity condition of that evolution of that state psi. So if system doesn't interact with this system plus that, so it doesn't change the causality. So even though A may be performing measurements on the system, even though this A may be performing measurements on the system, but for B, the causality should hold. That's the point. So now there is a conundrum. So there is an observer, there is a system in which there is an observer and the system, and there is another observer who is sitting outside. So for this subsystem where observer and system is there, so we can say causality is being it holds, and the same can be said about a system observer who is sitting outside, who is oblivious of whether the observer is out measuring things or not. For him also things. So if it's a quantum observer, the question is things should also hold. For example, so now the question is for the observer B, so he's also observing. So he's oblivious of what's inside. Now here comes the point. Now the point is, so longer as B is not is not doing anything else, so his he will have some measurements. The point is that so B will have measurements which is oblivious of whether A is measuring the things or not. Now the point comes here. The point comes once these two observers are going to check or cross-check things with each other, or their measurements with vis-a-vis each other. So there comes the point. So the question is in the dramatic sense, for example, the way we have in this thing. So if B checks, for example, in the way the book has tried to see it, for both observers, an observer trying to measure process 1 and observer trying to measure process 2. And observer 2 also trying to measure process 1 observer 2 trying to measure process 1. In both cases, the point is that how can does observer 2, so for example, if we have a time lag of 1 week or 1 day or twice, so observer 1 is having some measurements, but observer 2 is oblivious of whether observer 1 has been measuring things or not. But at the end of 1 week or at the end of 5 days, 7 days, he is going to just come out some measurement, some values. For observer 1, he is also registering or measuring things time to time from 1 week to 1 day, 2 days. He is daily counting the things. Now the point is, do the two observers, this quantum mechanical, this observer, and already the observer is sitting inside, who assumes that causality is holding, do their measurements, should they agree or not? Or whose measurements are more authentic or more valid or more closer or precise in their measurements. So this is the point. Or should they agree? Should the measurements of the observer sitting outside the system, or the observer who is measuring system and that isolated system, should they agree? Or there should be what I should say for the way so this is the point. So if you formulate, for example, so what observer BA will be saying that he has measured something. So in the process of measuring something, that state psi. So it's in the process of measuring something. So how does state function psi? What I should say. So the question is the whole this construction of before we are going to construct the universal wave function. So this idea, it all depends upon how the observer and the isolated system and the observer, who can be quantum mechanical observer sitting outside, who is also measuring the same thing. How, or there can be more than one observer, how they are going to measure things, and whether their measurement should agree or not from a quantum mechanical understanding. So there can be various alternatives which we are going to So the conundrums of these alternatives, what are the alternatives for which both the observer, one observer who is observing the isolated system where causality holds, the state holds, or there is objective considerations in which causality is supposed to hold for one observer. For the observer who is outside this observer, who is observing the isolated system, so he is also measuring things. So there may come to be alternatives vis-a-vis how the observer or the observers who are trying to measure isolated system. And the other observer can sometimes, you can also invoke measuring apparatus through which he is trying to observe the system, isolated system. So there can be layers and many layers about how to interpret this isolated measurement of this isolated system. And those are the various alternatives which we are going to construe. And among the alternatives, there is one of the alternatives which is expounded by these authors. So before coming to what are the alternatives to describe the state of the system, for example, alternative 1, without the point is to just to make sense of a system with which will not only be explanatory in the broadest sense, but it will not be contradictory also in terms of agreements or even disagreements. So that's the thing. So any scientific theory is considered plausible or more plausible if it irons out different contradictions with the simplest of assumptions, or the best theory is one which describes the world out there. But the world out there, it's also very thin. Whether the world has objective elements and it has subjective elements. So how best the subjective and the objective elements are synchronized, that would be said. Or if we use the words of von Neumann, which is part of this thing, which that's known as psychophysicalism. Means your psychological measuring of cognitive or psychological way of looking should correspond to the measurements out there, or our subjective considerations should have an objective description. Our subjective measurements, which are perceived by our these senses. Psychologically, how you just try to measure, they should correspond to our objective description. So before we are coming to alternatives, so we'll discuss one by one. The alternative one says that there's only one observer. So there cannot be or this is rather there is a word in English which is called solipsism, solipsist, or solipsism is a philosophy like my measurements, I become more important. So I as an observer, I or as a person who is going to measure, so my measurement is absolute, or an observer, what he filters out, his measurement is taken to be absolute. Whether that measurement is an isolated system or it can extend to universe as a whole also. So the idea of me, if I use literary language, me and my image, or me and measurement, they should somehow coalesce, or they should dissolve. The distinction of me and my measurement. So what me and my image, what the measurement of me, which can be seen as an image. So they should dissolve, or to use more scientific word, it's like so each of must us must hold the view that he alone, he or she or he alone is a valid observer, and its inhabitants for all time. So it may be more egoistic position in that sense, that you give weight to the or validity to observer or his measurements. So this is one alternative. So in this view is generally considered as consistent for both. You can this view not only makes observer inside who is measuring the isolated system, and observer outside. So they will what I should say, rely on their own observations or their own measurements. The point is whether the two measurements may agree or disagree. That's another thing. Which this alternative one should satisfy or not. That's also the case. So that may be a questionable thing. Alternative 2 says to limit the applicability of quantum mechanics by asserting that by asserting that quantum mechanical description fails when applied to not a single observer but observers, or measuring apparatuses. Or when the systems are approaching macroscopic sizes. A large systems, when the size of the system is very large. So this is the second alternative. So we can fundamentally assume that that quantum mechanical description fails when, so maybe no two observers will come to some common value of measurement regarding this isolated system and the observer outside. This is alternative 2. The alternative 3 says, if we just take alternative 3 says to admit validity of state function description but to deny possibility that B could ever be in possession of system A plus S. So to admit validity of state, so it's like it comes, the alternative 3 comes maybe a sort of a compromise of alternative 1 and 2, where we admit the validity of state function, but to deny the possibility B could be in possession of system A plus. So the quantum observer may not but to deny the possibility B could be or be in the position of, so quantum mechanical observer who is sitting outside can just totally, what I should say, encompass or have that capacity to measure the system plus that observer plus that isolated system. So maybe now if you come to alternative 4 says so now this is an interesting postulate. So it says that the state function psi, it's not you have not to abandon. So it's the antonym of the first one, the solipsistic one. That state function psi describes the state of the whole system. It is something. State function uniquely describes the state of the world, universe, or state of the state function. So state psi itself is supposed to be composed of many alternate states, and their superposition will give us the description of the single system. Or state psi is composed of ensemble of systems, which is not a description of single system. Description of single system. It's not a description of single system, but ensemble of systems. And probabilistic assertions arise because from the incompleteness of the description. So we can have the statistical notions of statistical mechanics. They can come how from statistical considerations we can have ensemble average about a given measurement about a system, and the probability incompleteness can be said because we discuss things in the probabilistic sensibility. So alternative 4, now we are jumping to alternative 5. So alternative 5 assumes that without any, so it has some, so the alternative 5 says that, so that just like, so we have the state psi observation processes, which are completely described by state function. So state function psi of the physical system, it must include observer plus measuring apparatus plus this isolated system. So what is to be the state function? It not only includes observer, it includes measuring apparatus, and it includes that system which is going to be just measured. And in this one, maybe we can also have the role of some hidden variables or elements which will which you can also assume some non-local elements or hidden elements which are there, which will make the system complete. That can also be one of the alternatives, which can be implicitly assumed, and there can be various theories like non-local theory, Bohm theory, so they can also include those alternatives. And maybe there can be alternative which the book has not discussed in that much. So Bohr's alternative, that a state function psi takes the value the prior or posterior in that sense. The state function psi then it takes the value, the eigenstate takes the value, and the operator operates on the eigenstate, the eigenvalue. So our measurement decides what is the state of that things, state of eigenstate, state function, what is the value it's going to take. Prior to it or posterior to it, what the state function was, or what the state function would be. So these questions become irrelevant in how we identify this wave function. Yes. So before coming to how what is, so this maybe this alternative 5 maybe how what the authors would write to say. They are interested in that thing. So So the theory of universal wave function. So among these 5 possibilities, these the what I should say, the central idea or theme which we are going to write is that this thesis or this study which we are going to follow is going to show so underlying theme of this thing is going to show or devoted to show what the universal wave mechanics together with correlation machinery for its interpretation forms a logically self-consistent theory description of universe with several observers at work. So the universal wave mechanics together with the correlation machinery. Correlation machinery means the state psi. It's not. It's being correlated with that measurement observer or the measuring apparatus. For it, so universal wave mechanics, which is to be seen and which is seen in one of the postulates, which includes observer and measuring apparatus. Includes observer and measuring and plus isolated system, all three together. That constructs for us the universal wave function, and it's how they correlate forms a logically consistent scheme. And there cannot be one observer, there can be many observers. Like that onion analogy. wheels within wheels, or what I should say, observers being what I should say, ambushed by observers. Ambush is a bit cruder term. I would say observers being escorted or being seen by other observers in tandem or in succession, or in what I should say, in succession, spatially as well as temporally. You can also take it. Because the state function is going to evolve in time, and there can be succession in terms of time also. That's it. So here there is one important point which is going to say something, is that subject to experiences, subject to appearances of such observers. So they are going to lead to something novel situation where formal theory is objectively causal and continuous, and subjectively discontinuous and probabilistic. So we started when we defined the system isolated state, which was this observer assumes that isolated system to be objective and causality should hold. But once a person is going to measure something, he will different observers or a given observer will have measurements which may disagree with each other. Subjectively, they will agree to their own individual observations, but these different observations will disagree from observer to observer. So this is what I was saying. So you have theory should have synchronized or synchronized objective and the subjective descriptions. So even though the theory assumes to be objectively causal and continuous when it's not untinctured, but it can be subjective, so we can accept it can be subjectively discontinuous when measurements are made, and it's probabilistic also. And there cannot be one systems, there can be many subsystems. If we borrow terms, or if we borrow things from statistical mechanics. So if we consider things from statistical mechanics, or where we use how ensembles evolve in that sense. And because the language of subsystem and system, how relationship of system and subsystem, because in subsystems there may be copies of different ensembles which may be having an evolution which depends how their evolution can be. So in the same way, if you take that analogy for a subsystem, which is which may be a composite system in general, for example, a single pair of subsystems, single pair of subsystems can be represented by superposition of such states. But for example, if you have a Schrodinger wave function psi, which has x1 and x2 pair of particles, can be always written as, you can write psi of this can always be written as phi of x1 neat of x2, but only in the form size that you can write. So you know in quantum mechanics how you can relate a state psi and phi via some operator or via some what I should say operator, so that we can relate two states of two states. How we can relate two states psi or phi, but if there are, so you can always relate them as psi can be related as ij, aij. So this is, you can take it matrices or you can take it as an operator state, x1 phi neat of x2. These I and j can be symbols. So in later case, for example, I and j cannot be alone, but they can be assumed, they are superpositions. They are superposed states in that sense. So you have to see evolution of one subsystem vis-a-vis related to other subsystem, which may also be in evolution, to be in that sense. So, and such correlations may arise when systems are interacting with each other in that sense. And our composite system consists of observer plus object system. I'll just write one sentence and then this will in some sense see what we are going to do. So you can say we can say that each element of resulting superposition describes an observer sorry, I'll just write it. This is more. each element contains a definite observer, a definite observer, state, and definite relative object system state. So each element consists of an definite observer and state of definite relative. So an observer is a part of that entire system in which the measuring apparatus or observer is seeing some system relatively. It's also evolving. It's not also static. So in that sense, so it's not only measurement of your state, but it's how subsystem and your system they are correlated in some sense, and your measurement is part of that subsystem, relative subsystem, measurement of your system and the subsystem, relative subsystem. That's also taken in that configuration. How we are going to how we are going to construct a measurement of a system in that sense. So in the next series of, so this was today's, if I summarize what we have done today is that we have tried to see how state functions psi, how we just can see its construction as an isolated system, as an observer or many observers trying to measure its evolution. In the background of how we can objectively construct state psi and it's obeying some causal order to begin with, which may be objective. It has to be seen or it has to be flashed back around a reality where an observer is going to measure that supposedly objective reality, which has causality and continuity embedded in it. And that observer can also be, sometimes he can be individually unique observer, or there can be many observers observing the system behind. So these different measurements may agree or disagree, or how we even just record the measurements, agreements or disagreements. There can be various relative interpretations, 1, 2, 3, 4, 5. And one of the interpretation which this recurring theme of what we are going to study is we include apparatus plus observer plus measuring, so that together they form one correlated system. So now in the next series of lectures we are going to just continue with our what we have started with. Thanks for listening.